All right, go to. Right, hope that everybody can hear me. Hi everyone, my name is Tingjun Chen. I'm a faculty in Duke ECE. So I mostly work in the general areas of networking and communications with a focus on physical layer technologies for 5G and beyond systems. My PhD work was mostly on physical layer technologies, including millimeter wave transceivers, massive MIMO antenna systems, edge computing, and also SDN control systems for heterogeneous networks, crossing both wireless and wired domain. So if you look at this picture here, this pretty much resembles what Suma and Ira and everybody was talking about before. We have this overall network architecture that goes from the core network. That's where data gets delivered from the internet through the access network all the way to the end users. And then we can pretty much run all kinds of services and applications through these wireless and mobile networks. If you look at this picture, we're living at the edge of the network, but there are actually a lot of fiber optic cables, which are the blue lines here across the network. And one of my research right now is actually looking at the performance of these optical systems and how they can be interconnected and correlated with the wireless and mobile services that runs on top of the system. So 5G and 6G, in order to meet the requirements of higher bandwidth and lower latency, we actually need a very flexible and intelligent networks in the optical domain. And there are many technologies and hardware existing for many, many years that can support these type of technologies. For example, we have wavelength division multiplexing, which allows you to basically separate signal streams and put signals on different wavelengths and let them send across the same fiber strand. We have an erbium doped fiber amplifier. These are basically optical amplifiers that can actually bump up the signal to make sure the optical signal quality maintains as it propagates. Oh, sorry. The problem with the Zoom. Yeah. So I forgot to share the screen. Yeah. Yeah. Right. Right. And then I have to do this again. Yes. Hope that's gonna be fine. Okay. Cool. And also we have optical amplifiers, which are able to bump up the signal, let's say every 30, 40 kilometers, to make sure the data can be delivered with high quality to the other side of the network. But many years ago, even current networks, many of these optical services and hardware are actually deployed in a fixed manner, meaning that they cannot be reconfigured in real time. They cannot be intelligent in order to support different types of requirements. So that's why we envision that moving from LTE, let's say 4G to 5G and 6G, we actually need a more flexible and intelligent optical networks in order to connect the core network and internet to the end users and services. So if you look at how the data gets through the core, through the distribution and access network, all the way to the sites and users, we can actually put services and data streams on different wavelengths. Let's say we put gigabits passive optic networks on lambda 1 that can go to, let's say, fiber to the home on the right-hand side. We can put LTE signals on the green wavelength and it goes through the network to the E node B for LTE. And also we can put 5G services, let's say on the purple light wave, and let it go through the network to be going through the G node B for 5G and beyond networks. And one key component here in all these distribution networks is actually what we call a ROADM, which is essentially a piece of hardware that can allow us to do reconfigurable add and drop options on different wavelengths. So on the left-hand side, I'm showing a piece of hardware from Lumentum. It's actually being deployed widely in different production networks. And on the right-hand side, you can basically see the diagram of what's actually inside this Lumentum ROADM unit, which has several key components. The first one is the wavelength switching, wavelength selective switch, or WSS. Essentially, it's basically a fiber brag gating that can basically separate wavelengths and then use a MEMS mirror to direct wavelengths to different output ports. That's how we get wavelengths separated from the single fiber strand to be able to carry signal and send the signal to different ports. The second important component here is what's called the EDFA, which basically amplifies the signal and make sure the signal quality stays high as it goes across the optical network. And when we have these different ROADM pieces, we can essentially construct a ROADM network with many high degree ROADM nodes. For example, you can have a west degree ROADM connected to the east degree ROADM. You can do all kinds of add and drop options here depending on the service request. You can, let's say, add the traffic from a cellular site here to let it pass through the network to go to your baseband, your edge data center. You can also drop a signal here on a certain wavelength, so make sure you can actually deliver the service to your desired site. And this is how basically ROADM sites are being constructed and used. So there are many challenges here in basically operating and maintaining and monitoring these type of systems, just because there are so many wavelength channels that have to be monitored and configured in real time. There's also nonlinearity and imperfection of the hardware coming from the physical property of these devices, especially the amplifiers. And also, if you look at the different channels on these, for example, optical bands, actually there's usually inter-wavelength interference and also crosstalk between adjacent channels. And also, if you have multiple of these amplifiers connected in a cascading manner, you also got this sort of the filter narrowing effect. The signal quality basically gets degraded as it goes across several hops in the transmission system. So one thing I'm working on right now as part of the Athena Institute is looking at how are we able to basically characterize and understand the performance of these amplifiers in the optical domain, so that we can basically make better control and smart configuration of them to make sure we can deliver high quality services across these long transmission systems. So as Ian mentioned, so we actually have been collaborating with a lot of the national testbeds here in the US. And part of my PhD work from Columbia was involved in building and deploying these Cosmos testbeds as part of the National Science Foundation platforms for advanced wireless research, where basically we built a programmable optical network composed of several programmable hardware pieces. Here you can see there's a central optical space switch. It acts like a layer 2 switch in the optical domain. We have add drop ROADM units here, which I was talking about before. We've actually got dark fiber deployed across Manhattan. We can use to run various kinds of measurements and also edge computing experiments. And here, this is basically the data center as part of testbed, where we got an entire optical rack with several optical equipments. We got another entire compute rack where we can connect the optical components with servers and switches to run all kinds of experiments. So one thing I'm looking at right now is basically try to use machine learning approaches to characterize the gain performance, or how do we basically do better gain prediction for these optical amplifiers. For example, if you look at how these amplifiers are being used in the transmission system, you typically get these long fiber spools that connect two sites, and then you have to actually bump up the signal before you launch the signal into the other side. So basically, we actually want to make sure when the signal gets launched into the fiber, the spectrum somehow maintains flat in order to deliver better service quality across different wavelength channels that carry different signals. So one thing we're looking at is basically to do a lot of data collection on these commercial grade ROADM units, which is being used by various service providers and production networks. And we're able to actually look at the entire space of the configuration. If you actually want to do machine learning, you need a very high quality data set for training. But if you look at the total number of state configurations in such a system, you get to the very extremely large number of state space that you cannot sample through for a machine learning task to run. So that's why for these specific tasks, we look at randomly sampling different channel configurations of a dense WDM channel and see how can we use some of these sample data set to do a better prediction of the optical performance in these amplifiers. I'm just showing here some example data set we've been collecting over the past month on different amplifiers deployed in testbed. These are all commercial grade amplifiers being used in production networks. And we're actually able to see the difference in terms of the amplifier performance as a function, for example, with the channel loading, with the input power levels, and so on. And we're able to run a simple neural net with 5 fully connected layers to basically show that we're able to predict the gain ripple, basically how much the measured gains differed away from the predicted gain. And by using such an approach, we can basically try to tune the channel attenuation so that we can make sure when the signal gets launched to the long transmission system, all the channels are having relatively equal power to make sure the optical transmission is with high quality. So I'm going to stop here, and we're going to look forward to work with AI folks' expertise and also people from other areas to make these optical networks more intelligent and reconfigurable for other services and networks in 5G. Yes.